If you look at the molecular structure of many of today's most successful drugs, you'll spot a common element, fluorine. For decades, medicinal chemists have used it to make drugs more stable in the body. The common wisdom says it's because the carbon-fluorine bond is just incredibly strong, acting like a kind of chemical shield. But what if that's not really the whole story? Let's dig a little deeper. So, where are we getting all this from? Well, our analysis today is grounded in a really rigorous perspective that was recently published in the Journal of Medicinal Chemistry. And what the authors do is challenge that conventional wisdom, offering a much deeper, more nuanced explanation for why fluorine is such a superstar.
Here's how we're going to break it down. First, we'll see just why fluorine is such a popular tool in the first place. Then, we're going to tackle that common myth about bond strength head-on. After that, we'll meet the enzymes that are actually responsible for drug metabolism, and then we'll get into fluorine's true influence, based on some solid physical-organic principles. And finally, we'll see how all this leads to a much more rational way to design drugs.
Okay, so let's start with the basics. Just how important is adding fluorine or fluorination to the whole process of creating a new medicine? Well, it's one of the most common moves in a medicinal chemist's playbook, especially during lead optimization, which, by the way, is the most expensive part of preclinical drug development. Strategically adding a fluorine atom can totally change the game. It can dramatically improve how a drug behaves in the body, which is what we call its DMPK profile.
And this brings us right to the heart of our discussion, that popular but, as it turns out, scientifically incomplete explanation for why this strategy works so well.
This quote from the paper just gets right to the point. The authors argue that by just saying, oh, the carbon-fluorine bond is strong, we're ignoring the really complex and fascinating reality of how our bodies metabolize drugs. It's a convenient story for sure, but it's not the whole story.
So here it is, side by side. On the left, you've got the common belief. It's a simple blocking idea. You just swap out a weak CH bond for a super strong CF bond, and boom, you've built a wall. But the scientific reality, over on the right, is so much more elegant. It's not about a simple block. It's about how fluorine subtly changes the molecule's fundamental properties, and that, in turn, changes how it interacts with our body's metabolic machinery. And here's our first piece of hard evidence against that simple myth. There are these studies that use a technique called the kinetic isotope effect, or KIE. It basically measures how an atom's mass affects the speed of a reaction. And what these studies show is that CH bond strength isn't always the deciding factor. If it was all about bond strength, you'd see a really consistent pattern, but the data just doesn't back that up. Okay, to really understand what's going on, we need to shift our focus a bit. We have to look beyond just the drug molecule itself and meet the key players inside our bodies that are responsible for breaking these drugs down. And here they are, the cytochrome P450 enzymes, or CYPs for short. You can think of them as the workhorses of drug metabolism. They're mostly found in the liver, and this huge family of enzymes is responsible for almost all of the oxidative metabolism that prepares drugs and other foreign compounds to be cleared from the body. This image gives you a great look at their structure. Even though there are a lot of different members in the family, their core architecture is remarkably similar. It's highly conserved. And most importantly, see that magenta structure right at the center of each one? That's the heme group. That is the catalytic heart of the enzyme. It's where all the action happens. So what do they actually do? Well, this diagram shows some of their handiwork. They perform these key chemical transformations, like adding an OH group, which you can see happening here, or maybe clipping off an alkyl group over there. The goal of all this is to make the drug molecule more water-soluble, which makes it a whole lot easier for our bodies to flush it out. All right, now that we've met the enzymes, we can finally dig into the core of the argument. We can start to build a much more accurate picture of fluorine's true influence on a molecular level. So here's the crucial point. Fluorine works its magic in a bunch of different ways all at once. It's not just one thing. It's this combination of subtle but really powerful electronic and physical effects. It can change electron density, it can alter the strength of neighboring bonds, reduce the basicity of nearby amines, and even mess with how well the drug binds to the enzyme in the first place.
Let's get into the nitty-gritty with a key mechanism called the radical rebound. For a lot of CH bonds, the very first step of oxidation involves the enzyme's active site literally plucking a hydrogen atom off of the drug. We call this a hydrogen atom transfer, or HAT. This is a standard, well-understood process.
Okay, but what happens if we swap that hydrogen for a fluorine? Well, this reaction diagram tells the whole story. Trying to do the same thing, a fluorine atom transfer, is not just more difficult, it's thermodynamically infeasible. I mean, look at that massive energy barrier. The enzyme simply can't do it. So it's not just that the CF bond is stronger, it's that the entire catalytic mechanism the enzyme needs to use is completely shut down.
Fluorine's influence also spreads to its neighbors, but it's a really subtle balancing act. It can pull electron density away through something called sigma induction, which can actually strengthen a nearby CH bond. But at the same time, it can donate electron density through another effect called hyperconjugation, which can weaken that same bond. It's a delicate electronic tug of war, and the outcome really depends on the specific molecular context.
Now here's an effect that's much more consistent. If you add a fluorine atom near an amine group, which is a really common feature in drugs, it reliably makes that amine less basic. Its pKa goes down. And that chemical change has a huge biological consequence.
See, many CYP enzymes have these negatively charged amino acids in their active site that act like docking points for positively charged amines on a drug. By making the amine less basic, fluorine weakens that crucial interaction. The drug simply doesn't bind as tightly, which means it has less of a chance of being metabolized. It's a less effective handshake.
And look, this isn't just theory. Let's look at the real-world example of the hepatitis C drug voxilaprevir. On the left is an early version of the molecule with a vinyl group that was a metabolic hotspot. The medicinal chemistry team then replaced it with the difluoromethyl group you see on the right. This was a critical move that stabilized the molecule and was key to it becoming a successful medicine.
Okay, this all leads us to our final and maybe most important point. What does this deeper understanding actually mean for the future of how we design drugs?
This diagram from the paper's graphical abstract just sums it up perfectly. On the left, you see how adding fluorine changes a molecule's fundamental properties, its electronics, its bond energies, its basicity, and those changes then influence its interaction with the whole complex metabolic machinery in the liver, leading to the outcome on the right, a more stable drug. It's a systems-level effect, not just a simple shield.
The authors conclude with this really powerful statement, and it's basically a call for more rigor in the field. The simple CF bond strength story is convenient, but good science demands that we look beyond convenience to find the underlying truth.
So the ultimate takeaway is this. Effective, rational drug design isn't about following overgeneralized rules of thumb. It requires a deep, rigorous understanding of the underlying catalytic mechanisms and all the subtle physical-chemical properties that govern how a molecule will actually behave in the incredibly complex environment of the human body. And moving from that simple myth to this deeper reality, that's what enables true innovation.